Here we have an example involving vector-valued functions of one variable, t. So think of t as time, for example, and r might denote the displacement of some projectile moving through space, or in the plane in this case. We're given the following information. Let C denote the straight line segment from point A to point B. Two things are required. Produce a vector function, r of t, and a t interval, I, that parameterizes that curve C in the forward direction. So as time increases, your parameter time increases, we want to move from A to B along the straight line segment joining them. Okay? So there's a number of ways you can parameterize these kinds of curves, okay? What I try to do is provide the most simplest way. Okay, I think it's best to work with the simple forms and simple numbers, if possible. And part B and part C, you're given two different line integrals to evaluate. This is a scalar line integral, and so we're integrating here with respect to the arc length, and this is a vector line integral. Okay? Now to do part B and part C, you can see that in both part B and part C, the integrals are integrating over the curve C. So you definitely need to be able to do part A to do B and C. Okay? Unless it's like you can apply the fundamental theorem of line integrals in part C, maybe. Okay? All right. So part A, parameterize or describe the line segment. Okay. So if and you wouldn't write all this down, but let me just sketch. So I want to go from 1, 2 to 2, 1. Okay? So how can I describe that curve with the right direction, in the forward direction? Well, there's a number of ways you can do it. Okay? So in general, you may actually want to just commit one of the forms to memory. That's fine for basic straight lines. Or if you don't want to do that, you can easily derive it. Okay? So, how would you derive it? Let me just show you that quickly. Let's say I've got a point A and a point B here, and here's the origin. Okay, I can always calculate the vector OA. I can always calculate the vector OB. Okay, let's take a point on the line segment AB. What I'm interested in is that vector there where the point can sort of move around between A and B. Now, you can see that basically this orange vector is this vector plus this little segment vector of AB. Okay? Can you see that? So let's call this point P or something. So P is an arbitrary point on the line segment. So you can see that the vector OP is that vector, which is known, plus the vector AP. That's just the triangle law. Now the vector AP is parallel to the vector AB. It's just a multiple. It can go anywhere from 0 length up to the full stretch AB. So what we can do is introduce a parameter to get AP. That'll do it. So here T is your parameter. Okay? So back to our particular, so if you ever forget it, it's just the triangle law of vector addition for straight lines anyway. So let's get back to our problem. how can we adapt this to our problem here? Well, this is the point A. This is the point B. Okay, so R of t will be the vector OA, so up to there, so that'll be the vector, say, 1, 2, plus t times the vector AB. Now, how do we calculate a vector, given 2 points, how do we calculate the vector between them? Well, you take one away from the other. Okay, so the vector AB would be the OB minus OA. So the position vector of B minus the position vector of A. Okay, so that'll give us positive 1, negative 1. Now, if you wanted to write this out in I's and J's, that's okay. I've just written it as an ordered double here. Okay, so what is the t interval? This is a t interval. And what is the vector function? This is the vector function. Okay? All right, so if you want to go even a step further, you can combine this. Okay? And if you want to do I's and J's, you can do that there too. All right, so that was pretty easy, and I spent a fair bit of time deriving that, but you wouldn't take so long in the exam for something like that, of course. Part B, compute the scalar line integral of here. So this is the thing we're integrating. This is our integrand, the function of two variables, x plus y. And we're integrating over the line segment curly C on the sort of middle, in the middle section, the middle graph. Okay, so how do we do it? Well, this is a little bit more involved, and it relies on part A. Now, what is this ds here? Well, this is like, sometimes it's called the arc length element, okay? So what we do is we basically reduce this down to an integral that we know, an integral from high school, okay, that we can evaluate, all just basically in terms of the parameter t, okay? So, in general, if I'm integrating something like this, this is just expressed as an integral that we know from school just involving t. Okay? Now the little a and the little b are the limits of integration for your t variables. Okay? So if we look back to part A, that would be your a would be 0, little a, and little b would be positive 1. Okay? R of t is this function here. Notice that we have to compute its derivative and its length and multiply through. So, you can kind of think of this ds element as being expressed by this absolute, or magnitude r prime dt. All right, so what do we have to do to actually knock this over? We have to calculate the derivative and its length from this. We have to evaluate f along the parameterization, and then we have to do an integration. Okay, these kinds of problems are generally, very the same in their solution method. Okay. All right, so for our problem, so f along our parameterization. Now you can think of this as being the x component and this being the y component. Okay? So, basically what we do is we replace x in our f with 1 plus t. We replace y in our f by 2 minus t. And then just clean it up. Okay, so now what? Well, you can see that the bottom line is just a constant. Now, usually that's not the case. Okay, usually there is a t present, but just in this case it's very simple, so it's actually not present here. Okay, so what else do we have to compute? The derivative and its magnitude. So let's take the derivative by differentiating in a component-wise fashion with respect to t. So you differentiate the first component with respect to t, you'll get 0 plus 1. The second component with respect to t, you'll get negative 1. Okay? Again, this is a special case. The tangent vector, the bottom line, is a constant vector. Usually you have t's in there, but for this simple example, you don't. So what's the length of this vector? Square that, add them, take the square root. It'll be root 2. Again, sometimes there's t's at this stage. We don't have any, which is a not good place to be. So let's formally evaluate this. So let's call this, let's just call it I for, let's call it J, big J. Okay? So let's put everything together and find out what J is. So that is 3. That is root 2. So this is a great place to be now because there's no t's whatsoever, but in general you will get t's here. So the value of this is just 3 root 2. Any questions? Now sometimes you have to be a bit cunning to do the integrals here, but for this one, it's pretty nice. It's pretty nice. Okay, part 3. If we have a vector field now, so the output of our vector field is a vector defined by xi plus yj, then compute the line integral over the line segment C in the forward direction. Now remember, with line integrals, direction matters. Okay? The way that your parameterization, or the direction that your parameterization covers or rolls out your curves makes a difference. Okay, direction is important when you're doing line integrals. Okay, so let's see if we can polish this one off, and then we'll be finished. Now, I guess our general expression when we're sorting out one of these line integrals, it's very similar to part B in the sense that you evaluate the given function along the parameterization, but you've got a dot product now rather than just scalar multiplication with a magnitude of the tangent vector r dash. Okay? So we've got this bit in part B. We already calculated the derivative, it's there. So to roll this out, all we need to do is calculate f, the vector field, along our parameterization, and then just do a basic dot product, and then we just do a simple integration. All right, so Like I said before, what you would do is you imagine x is this, 1 plus t, y is 2 minus t. Go up here and replace x with 1 plus t and y with 2 minus t. Okay, so I'll get 1 plus t I plus 2 minus t j. All right, so what we're going to do is take that and dot it with that. Well, I guess I'm going to write these all as just ordered doubles. Okay, so instead of having the i's and j's here, I'll just write it as an ordered double, just to be consistent. Okay, you can write it either way. Okay, so let's take f, evaluated at r, dot it with the primed or the tangent vector, and then we'll do a simple integration. So let's call this capital K. So it's the dot product of that with this. So we just simplify the dot product, and it's a basic, hopefully a basic integral to evaluate. So we're going to get something like 2t minus 1. So the last step is just to knock over this integral. So let's see if I can squeeze it in. The last term is going to be 0. So I'm going to get 0. Now, is there a better way of doing this problem? Even though I've used part A and a little bit of part B to solve part C, is there a better way of doing it? Seems like a lot of trouble to go to get 0. Okay? So my question is this a gradient field? Is it a gradient field? So in part C, is the vector field f the gradient of some other function? Is it? What happens if I Okay, so I'm asking, is there a phi such that the gradient of that phi is f? Anyone know? Yes, so what would a phi be? Yeah. So the answer is yes. Okay, if you take the gradient of that phi, you'll get xi plus yj, which is exactly the gradient field that we have here. Okay? Hence, we can use the fundamental theorem of line integrals, the Footley What is the fundamental theorem of line integrals? It says that if you have a vector field, big F, and you're integrating there over a curve, essentially, if that vector field is a gradient field, all it is the gradient function at the endpoints, okay? Just the integral depends on the endpoints, not the path between the 2 points, okay? So, okay, that's what I mean when I talk about the fundamental theorem of line integrals, okay, where phi is the gradient of phi is f. Okay, so for our problem, let's see if we can work it out. Okay, phi is this. So phi at B is that. So if I plug those into my phi, I'm going to get 2 squared plus 1 squared all over 2 minus 1 squared plus 2 squared all over 2. So what have we learnt from this? Sometimes there's a better way to solve these line integral problems. Okay? So we will conclude that our line integral, K, is just 0 from the fundamental theorem of line integrals. Now, which method would you rather go through? This one, which is, admittedly, you've got to choose the vector field, the potential function, the phi. It doesn't always exist, but if it's there, you should use it, right? You should use it. Okay? Now, on the other hand, you could argue, well, Chris, I already parameterized everything from part B and part A, so why not just continue through? Yeah, you can do that as well. Okay? It's up to you to choose an appropriate method that you feel comfortable with.